Hello everyone, long time no see. In the following weeks, I will gradually make a series of videos about vector calculus. This video is the first one in this series, and our topic today is vector field. Here are some usage about vector fields. For example, it can describe the flow of wind, the heat flux of a house, and the flow of water in a river. Vector fields are everywhere in our lives. So what is a vector field? Well, here's the definition of a 2D vector field. Let D be a set in R square, and R square is a plane region. A vector field on R square is a function f that assigns each point in D a 2D vector f. But what about a 3D vector field? Well, it is pretty similar to that of 2D vector field, except R square should become R cube, and point xy should become xyz, and a 2D vector fxy should become a 3D vector fxyz. And we can also break f into different parts that describe the change in x, y, and z to make it more clear. So here is what it is like. So it can be written as pxyzi plus qxyzj plus rxyzk. Here's an example about a vector field, which is a gravitational field. So object A with mass capital M is at the origin, and object B with mass M is attracted by A. The position of object B is x, y, z. So the force experienced by object B can be written as G capital M times M over R square. But at here, it is the scalar form of the force. So what is the vector of the force? At here, we need to add the directional vector of object B with respect to the origin. So the unit vector of the directional vector will become minus r over the magnitude of r. So r is the directional vector, and this becomes the unit vector of the directional vector. And here's a minus sign because the directional vector points to the origin. In this case, force becomes this one. And at here, we can just break it into separate parts with respect to x, y, and z. And at here, r equals to the square root of x squared plus y squared plus z squared. So f becomes minus m capital M G. It is a pretty long expression, and this shows the gravitational field of a certain point. This shows the force experienced by a certain point in the gravitational field. Next, I'm going to introduce the gradient field. So the gradient vector of a point xy on the function f points to the direction that f increases most rapidly. In other words, it points to the steepest slope of f. And according to its definition, the gradient vector of a point xy on function f can be written as the partial derivative of f with respect to x plus the partial derivative of f with respect to y. So it is clearly a vector field. And remember that the gradient vector of certain points will be very long if the contour lines of function f are very close to each other, since this is a sign of f increasing very rapidly. But if the contour lines of function f are very far apart, then the gradient vector will be very short. At last, I'm going to talk about conservative vector field. A vector field f is conservative if it is the gradient of some scalar function f, and f is called the potential function of f. Here's a very familiar example of conservative vector field. And again, it is gravitational field. The potential function of gravity is gravitational potential, and it is a scalar. The gravitational potential energy on an object gains during its motion only depends on its starting point and ending point. It has no relation to the path the object takes to travel between these 2 points. Therefore, the gravitational field is a conservative vector field.